All right. Is that big enough for people in the back to see? Do I need to make it bigger? Sorry that it's dark background with light characters. My dot files are set up for Solarized Dark. So we're going to run through the server-side implementation of the code here. Yeah, make it a little bigger. Yeah, absolutely. Oh, actually, it's not even full screen. What's going on there? How's that? Cool. Okay. So we're going to start out by looking at the signal handlers for the Django models. We have a post-save handler and a post-delete handler. On save, we have to determine if it was created, and that will give us our HTTP method, whether it's a post or a put. And then find URLs we'll cover in a minute. It's basically a helper method to access the model class to API endpoint mapping registry that I talked about before. So we just iterate through all the paths in that registry, create a channel based on the HTTP method and the path, and then ask Redis if there are subscribers for that channel. And if there are subscribers, then we use Django's URL resolution to resolve the path into a view function with arguments and keyword arguments, which basically gives us everything we need to call the view and get a payload back. Because Django REST framework is tightly coupled to the request response cycle, we have to do a little bit of magic in mocking up a request from Django's test request factory and stuffing an auth user in there that's like globally allowed. So the super user is staff true. That's kind of messy. I wish that our API code could be decoupled from the request response cycle, but it is what it is. So in the end, we end up with a response object after calling the view function and calling its render, that then we can take the content, if that happens to be a 200 response, and send it to Redis, publish it to Redis on the method channel that we had defined previously as the combination of the HTTP method and the path that we had rendered out. So yeah, all of that should be pretty much as I described it. Obviously, we have to handle deletes separately. Deletes have no response body, so we don't have to actually render any views for deletes. We just send an empty JSON body to the same method channel being the delete method, and the same path from all the paths that were in our URL registry. Yeah, has subscribers is handy there. Numsub is a subcommand of pubsub for Redis. It's interesting to know. So that gives you an idea of our data isolation strategy. So let's jump over to our registry. For this example, I made the models as simple as I possibly could. So we have this like to-do list sort of thing with some text and whether it's done or not. It's just a single model. So the URL registry is sufficiently general enough to be able to express pretty much any URL that you want to. But in this case, we're just registering detail methods, which are put, patch, and delete, though we're not really using patch. Mapping those to the view name to-do detail, which is our API view name for to-do items, to resolve based on the primary key of the model instance. And the list method, which is a post, which I'll explain in a minute. We're essentially kind of like cheating here and appending a query string argument to filter the list down to only the single item. Yeah, I'll explain that more in a second here. So the URL registry, register is pretty straightforward. We just have this like global registry, model registry here. And we're registering a model class in this inner decorator to all of the HTTP methods and the lookup function that is used to actually render the API endpoint. So all of that goes into this global model registry when we call register. And then helpers that you saw primary key and primary key filter. Primary key takes a view name and returns a function that will call Django's reverse, which basically takes a view name and turns it into a URL path, whose keyword argument is the primary key of the model instance that we pass in. Again, primary key filter just appends a query string based on the primary key field of that model instance to the view name. So that is all of the model registry stuff that has to happen on the API side. So now you should have some sort of sense of generally how we use the post save and post delete signal handlers to render a list of REST API endpoints according to the conventions of the HTTP method and the model class that we registered in our URL registry. If we wanted to add more, I guess, subscription channels here, we would just need to make sure that we registered the model with the appropriate HTTP methods in order to teach the URL registry how to resolve those API endpoints. Switching over to, actually, let me ask, are there any questions about that implementation? I know it's kind of a quick overview. I don't know how many of you are familiar with Python and Django, but I would assume that Rails and other MVC frameworks have similar capabilities. So does that kind of make sense? That URL registry model signal handler approach? All right, so let's jump over to the stream producer, which is in Node.js. So Node is pretty much acting like a bridge here, bridging the publisher-subscriber model, consuming from Redis and just piping it back through to WebSockets. We're using Socket.io over WebSockets, and we have a Redis client. So you would expect to see a lot of registering of events from the Redis client and registering of events on Socket.io, and that's pretty much what's happening here. So when Socket.io gets a connection, it automatically it waits for an auth event from the client, which is the access token to use to make these head requests to the API, and then it waits for subscribe events from the client. So that the client asks Socket.io to subscribe it to an endpoint, and so we're actually proxying Node in front of our Django API because we serve our initial payload from Node.js, and so to avoid cross-domain API requests, we proxy the Django API through Node. So it comes back to Node and then through to Django. So that's why you see hostname localhost here and some a Django port environment variable. So all that to say, we either make a head request or a get if we want the body for some reason along with it. And if that comes back as a 200, then we register the subscription with this global listener of pub/sub channels. And yeah, we push the socket into that channel listener's global so that we can register the socket with the pub/sub channel. And so then on the Redis side, when we get a message from Redis via pub/sub, we know the channel and the message. We look up all of the channel listeners from this subscriptions global on that channel, and then we will iterate through them and emit a socket event on each of their sockets, saying that we're sending a payload down with this channel and with this data. So all this is glue, right? It's just like piping pub/sub from Redis to Socket.io to get down to the client, allowing the client to ask to subscribe to channels, and we have this kind of gatekeeper in between that checks the authentication to make sure that that user actually has access to that endpoint. And So this combination, this like dance between Django and Redis and Node.js is the entire server implementation of this concept. Yeah, you can see the Frenet decode. Frenet is a symmetric encryption library that Heroku developed. Redis doesn't have TLS support, and it seems like it never will, so we make sure we encrypt everything because Heroku add-ons go over the public internet. So yeah, let me go back to the presentation here. Let's see if I can unmirror displays without catastrophe. No catastrophe. Sorry, I seem to have lost my browser window. All right, that's probably going to happen again next time I switch to doing code viewing. So that's the server. Again, any questions about that implementation, either the pub sub bridge on the Node side or the Django REST API integration? Cool. Well, let's start talking about the client. The client here, to me, is the more interesting bit, or definitely the more fun bit for me. So we chose to use React.js on the front end, and I couldn't help but talk about it because I feel like it's a really useful match to the kind of paradigm of data flow that we're dealing with this technique. Of course, you can see that you could use any RESTful API backend that you want. You can use any front-end technology that you want. The important part is that the client stream consumer acts as a pub sub subscriber to channels based on REST API endpoints to the server, right? So there's nothing saying that you have to use React, that you can't use Angular or Ember or even Backbone or anything like that. And that I believe is one of this technique's strengths. But I think React, especially if you go whole hog and introduce Flux and Immutable.js, is really an ideal choice of tech for this particular purpose. React is built for data mutations, right? It's built to keep your client state in line with the presentation layer. It handles the propagation of that state down through hierarchies of components extremely well. And because React effectively re-renders your every single component that it needs to, every single time state changes, you know that your UI always accurately reflects your client state. And it's able to do this via the Shadow DOM. This is probably not news to anybody here. It's been very widely talked about. So React team found out that no matter how they structured their application, the very slowest part of interface changes was DOM mutations. And so they said, well, let's take our current DOM, re-render the components in a new DOM that's not actually connected to the browser rendering, and diff them and find the smallest number of DOM mutations we can and just apply those. And it sped things up enormously. Ember is including it. It's great. It has virtually no downside that I can think of. So that makes it fast to re-render on every single state change. React also supports rendering via server side, which for any client that is a consumer of an API is an enormous positive thing for time to a usable page. Because you have your shipping of your static assets down to the client. You have all of your loading of JavaScript and CSS and all that. needed for a normal web page to begin to work. But then for a client that is solely getting its data via an API, you then have an additional step of requesting all of your initial data, like bootstrapping your data. And that's another at least one HTTP round trip, if not many. If you can do it on the server side before you ever ship your client down, you're just that far ahead of the game. This isn't directly applicable to the talk. I just really think it's cool. But most importantly, the one thing from the React slides that I want you to remember is that React focuses on a unidirectional data flow with one-way data bindings. And this is extraordinarily important for our use case. I would say even in frameworks that allow two-way data binding, like Ember, that if you're going to use this technique, do not use them. Use one-way data binding. You will save yourself so much headache. Just think of the complexities that the two-way data binding would introduce to an app whose state is being pushed to it. I don't even want to consider the edge cases that would arise. Anyway, unidirectional data flow is basically a guarantee that all data coming into your app, no matter the source, will propagate correctly and be accurately reflected in your UI. So most people are familiar with the basics of React, I feel like, by this point, but Flux is something that a lot fewer people have dug into or understand, and in fact, I feel like it's still kind of shaking out a bit, but the core pieces of it are pretty well understood and pretty useful to a client architecture of this sort. So let's talk about each of the components of Flux for a second. Views are basically React components. In Flux architectures, they're commonly nested in hierarchy. So a parent view will get state. It'll call set state on itself. That will cause state to be propagated down to child views, and then they will call set state and propagate all the way through the hierarchy of components. Stores in Flux are similar to models, but think about them more like a table rather than a model instance, right? So it's like all the data your client knows about a type of thing. Stores will register themselves with the dispatcher, which I'll talk about in a second, so that when any data changes, the store is notified. So when the store is updated, it updates its internal state, and then it emits an event that's commonly hooked into by the React component views to re-render themselves. So we're going from the end back to the beginning. So you've got the view, and you've got the store passing its data to the view to re-render itself. So think of the data as flowing from the store to the view. The dispatcher is a global singleton that, like its name sounds, is responsible for invoking callbacks registered by other components. So the dispatcher sits in front of the store, and when an action, which I'll explain in a second, receives new data, it calls the dispatch method of the dispatcher and hands the dispatcher that data. Dispatcher then emits an event that is registered by the store. So the data gets propagated from the dispatcher to one or more stores and then propagated to the view. So again, unidirectional data flow, dispatcher, store, view. In generic terms, an action's job is to provide data to the dispatcher. Its one job is to call dispatch with data. But practically speaking, you can think of actions more as your API client, right? So actions know about URLs. You'll have an action per RESTful endpoint, usually. And it's the action's job to get data from the API and then to send it to the dispatcher. So part of what makes Flux such a natural fit for our real-time channel is that all we need to do is get data to that action on that same handler for the endpoint, the REST endpoint, and then the REST from the action to the dispatcher to the store to the views will all flow downhill automatically. So once the data is in the action, we don't care where it came from. Actions typically map to REST endpoints, and so it's obvious why we would find that a natural fit for a subscriber model whose channels are also REST endpoints. Okay, so let's look at the client implementation. How am I doing in time? I think I'm almost at an hour now. I guess before we do that, are there any questions about React Flux, how it fits into this kind of paradigm of real-time RESTful? Yeah.
Have you ever considered like a core async channel set up for this? So keeping everything, but maybe swapping Flux out for channels like ECSP?
I've never used that before, but I could conceive of anything which is able to notify views of state change in a way that the views could then, effectively propagate down through the UI. Like anything that does that could potentially work well with this method. I'll have to look at that.
Just something that I heard David Nolan suggest, and I thought was really interesting because I've been doing a little bit with JS CSP, which actually also addresses that issue you mentioned where the stack gets blown on, runs out on an async.
Yeah.
So it's some interesting stuff.
That's cool. I'll want to follow up with you on that after the talk. Cool. Well, let's do the monitor dance again and dive into some of the client code here. So let's start with a store. You know what? This is not the commit that I expected. Hold on a second. Okay. Oh, live coding demos. Let's see. Yep. Store to do. There we go. That's our store. Okay. Back to Sanity. We've wrapped everything up for this real basic demo in a subclass of just basic CRUD stores and actions. So there's not actually much here except that we determined that the to-do store is registered with to-do actions as its actions, and then this identifier kind of gives us a key prefix to key off of the action names. So let's look at CRUD base here, so it'll be more interesting. All right, so we have stores know about actions because they have to be able to subscribe to these RESTful endpoints. So we have basically this is like a list endpoint RESTfully. This is a get detail. And then we have, hooks for getting all, getting one, for post and put and delete. So these are how stores react to these events sent to them by the dispatcher. So this all look basically the same. Ignore this case state stuff. I'll explain that in a minute, but basically just focus on the case where case state is synced. So we access our resources. We either update the resource or delete it or add it as is necessary according to the type of event that we're dealing with from the dispatcher. So we update our internal state, which is this dot under resources, and then we perform any subscription or unsubscription calls on the action. Again, the action being the kind of owner of RESTful API endpoints. It is who we have to ask to create and remove these real-time subscriptions of. So it has a subscribe resources function that takes an identifier. And remember, the actions here is tied to the actions for a specific type of object. So like the to-dos model, this is a to-dos store. It relates to to-dos actions. So this under actions is the to-dos actions. And you can see at the very end on all of these hooks, we are calling a function that causes the store to emit a change event that views listen to re-render. So post is similar. It gets a new resource and stuffs it into this resources and then subscribes to that resource and emits the change. Same thing with put, except that the resource already exists. So it's updating that entry and emitting the change. There's no new subscription happening on put because we're already subscribed to that resource. Delete, yeah, basically the same thing. We get the ID out of the payload for the existing entry, and then we remove that entry from resources. You delete this resources. We also unsubscribe from that resource from the action and emit the change. So that's the store part of our Flux architecture for this real-time interface. And again, because I'm giving you a very simple CRUD example here, our actual to-do store is just a subclass of that CRUD-based store. So let's go over to actions. Actions, to-dos. You're going to find a very similar story here where most of the logic is in CRUD base for the base for CRUD actions. We register here the same identifier for the action prefix key. And also, actions know about URLs, right? So we register a RESTful URL path prefix for this action, which it will then append to create the fully qualified REST endpoint URL for the individual actions themselves. We define an interface based on the properties of a to-do item, text and done, basically. We only allow posting of text, and then you can put an update done or text. It just puts together this data payload and then calls super. So we'll take a look at CRUD base in a second here. Yeah. Cool, so our base actions class, let's see, has these same post, put methods, all that sort of thing. You can see that it's putting together the URL for an AJAX call from the base URL, which we handed it in the constructor. Constructor, setting the base URL there. Remember that was /API/todos in our todos action subclass. And AJAX here is a promise. When the promise is fulfilled, we call dispatch server action, which notifies the dispatcher that that action has succeeded, and we pass it the data appropriately. So you're going to see the same thing with get. You see how we're actually appending the ID of the item into the AJAX call for a get request. Same with put. The URL includes the ID. Type is put. But the rest of it's pretty much the same. Once we get it back, we dispatch a server action. So this should look familiar to you in the sense of an API client, right? Like we've got a CRUD resource. We're putting together a URL. We're making AJAX requests. We're handing off the data to the dispatcher. once those requests are fulfilled. So then the part that's actually different is the subscribe and unsubscribe part. So in our base actions, we are actually handling the real-time subscriptions and unsubscriptions based on HTTP method and the relevant event for that method. So let's go to actions base. Right, so I'll get to the API subscription service in a second. Suffice to say, we've got quasi-private methods here for subscribing and unsubscribing to these channels on specific methods with handlers, and that defers to this API subscription service, which is passed to the actions, to the base actions. Unsubscribe just unsubscribes it from the service. So yeah, let's go over to the API service. All right, this is really the interesting part with regard to the real-time transport. Subscription service is an event emitter that takes an access token and opens a socket connection. So this is what opens the socket connection. As soon as the socket is connected, it'll emit an auth event with the access token that should look familiar to you, mapping to the pub sub bridge auth receiver on the Node.js side. And then it'll tell us connected, let's see. When we ask to subscribe to an API subscription channel, then basically we emit that subscribe event up to the socket and let the socket handle the subscription. Same with unsubscribe, we emit that unsubscribe event to the socket. We also want to add and remove listeners on that channel for our client socket implementation so that when we get data from socket.io, where is that bit? Yep, okay, so when we get data, we'll call handle set. Right, socket on set calls handle set, which simply emits. So again, this API subscription class is an event emitter subclass. So its job is to maintain internal state and emit events. So it emits set events on a given channel with a given data payload. That corresponds to the subscription mechanism on the base action, which stores hook into. So you can see this flowing from API subscription service to action to store. So that's how the data flows. Well, I'm sorry, action to dispatcher to store, because this is Flux. That's how the data flows from the WebSocket through the actions using the exact same action handlers as the REST API through the dispatcher to the store to the views. And just for kicks, we'll look at a component. There's nothing novel about this component. The only thing that we should mention is that on initial state, it bootstraps itself by getting all the items from the store. The store will then actually request all of the items from the action, which then once the action gets them, it dispatches them, and the dispatch gets back to the store. So this is store to action to dispatcher to store to views, and that's how the initial state is actually set. Right, and this store change bit is the view reacting to the store emitting a change event, and it sets its state, which causes the view to re-render. The rest of it is really straightforward. Does anybody have any questions about the client implementation here? Questions are my chance to drink water. All right, cool. So looks like I am at about 70 minutes right now. Let's see. Right, live demo time. this is really going to put the demo gods to the test. All right, cool. So I've got this, like really, really janky, obviously designed by an engineer to-do app that I can add or edit or delete items from. So what's actually going on here is you can see I can't scroll in or zoom in on the console stuff. You may just have to take my word for it. We have console messages that tell me that the to-do store has gotten all of the objects. And if we go back to, yep. So I disabled auth for the purpose of the demo, and now it's telling me it can't subscribe to a channel without an access token. So let's do a bit of coding in real time to further test the demo gods. What was that message? Oh, I see. It's running on the old. Yep. I had the wrong branch checked out. Okay. Let's wait for gulp to build and restart Node. Now let's see if it's happier. Yeah, there we go. Cool. So you can see we've subscribed to put and delete on all of these to-do items. We've also made head requests, which responded with 200 because I disabled auth, so everything is 200 right now. But the auth mechanism does still work. I just didn't have time to implement it completely for the demo. So the state we're in right now is that we used the REST API proxied through Node.js back to the Django REST framework to get all of our to-do items and then render our React component according to the get all from the store. So we've rendered all of our to-dos in a list right here, and we've also subscribed to changes on all of them. So if we were to replicate this in a new window and have them both displaying here, then I could select one of them and edit it. And when I edit it, it automatically gets pushed down to the other window via WebSockets. So you can see we received a Redis message with a JSON payload down from that put request. And you can see we still used the RESTful API to make the put request. So this is not communication via WebSocket from the client back up to the server to make puts and posts and deletes. Those are still happening through the normal API. But what's coming back down is through a WebSocket. This actually allows us kind of like a really cool, almost double entry accounting where we have some state on the client that we think is reflected on the server, and then we can verify that that state actually propagated through the system because we get the same message down from the WebSocket. Part of the reason I'm using UUIDs here is because then we can pre-assign identifiers to new items so that when we post a new item, the UUID is stable through the whole system. We get it back and can reconcile it with the item we just posted up. So all that works great. I could do the exact same thing from curl, from a Django shell. It doesn't matter where the data is getting mutated from. It just matters that the state mutation happens in a place where Django can hook into post-save or post-delete and do its whole URL registry dance and Redis pub sub. So just to show that this actually does work, there's a deletion, there's a post. The client generated this UUID, and if I were to slow this down, you would actually see this line grayed out and then become solid black. Remember the case states thing that I told you to ignore before. We came up with this idea to have a metadata layer on top of our actual stores, which defines a state for any given piece of data. because we want to be able to optimistically represent data to the user in the interface without losing the ability to reconcile that with the source of truth, which lives on the server, not on the client. So we have kind of this loading or deleting kind of pending states for any bit of data. When we get confirmation from the WebSocket, we move that to a synced or kind of like known state. And then we're able to know that the client is in sync with the server as far as its state. And that's pretty much the example app. I know it's not too impressive, but take my word for it that we are definitely using endpoints in Heroku Connect production where we have like dependency chains of views and of models. We have like foreign keys that define changing endpoints on their parents and all kinds of like crazy mechanisms that make this way more complicated, but the same basic rules still apply. We take our model instance, we define a list of URLs that change from that model instance changing. We use Redis pub sub to pipe the RESTful API payload down to the client via socket.io, and these subscriptions that our React app has asked the server to make on our behalf. So getting back to the presentation, if I can. Great. Let's take off mirrored. And go back to full screen. Sorry for the monitor dance. I don't really think it's avoidable. So yeah, I want to talk about some of the shortcomings of this methodology because it's not all like sugar-coated and greatness. You've seen the use of HTTP method throughout this presentation, but that's an extremely stretched analogy. It works really well for delete. It works well for put. It could work well for patch if we implemented kind of diffing of payloads and only sent the diff down. Post is the outlier because you don't know that you want to subscribe to a thing that doesn't exist yet. And so when you post a new item, the client doesn't know that it should be listening for that item, even though it may need to react to it in the user interface. And so what we've done is kind of cheated a little bit and published post on the list endpoint instead of the detail endpoint for the item that had just been created. And so you saw that primary key filter helper in the URL registry. That was us calling the RESTful API list endpoint with a filter query string argument, query string pk equals 1 or something like that, right? So that we get the response from the list endpoint with the single item that we care about back down to the client to know, hey, here's a new item. We could have a new set of items to say, like, I don't know, if we had like a sort of like a batch process that we extended REST to say, you can create these 5 things at once. Then we could extend that to say post to this list endpoint with IDs in 1, 2, 3, 4, 5, and it would send all those down to the client. The client would know about those new items and know to add them to its store and to subscribe to the REST endpoints based on those new IDs. But I want to be transparent and honest that HTTP method doesn't map one-to-one to this design. We've stretched it a bit for post. Yeah, clients have to maintain a list of their own subscriptions to the things that they care about, and that list can get really long. Anytime a WebSocket connection drops, especially because we don't have support for anything like sticky sessions on Heroku, everything is stateless in that regard, the client has to know what subscriptions it needs to resubscribe to when that socket connection comes back, because it could come back to an entirely different process, right? I mean, I don't know if I'm getting back to the same Node.js process that I was on last time, so I have to tell it about all the subscriptions. I would like to improve this and allow pattern matching on subscriptions, but I haven't yet figured out how I would relate that to user authentication, because right now, auth is so easy. If we get a 200 from a head request on the REST API, we know we're authed. But as soon as we move to kind of this star match kind of pattern of channel subscription, then we have to check auth when we receive messages, not just when we subscribe to channels, which is more difficult. So we haven't really done that. Yeah, so when you have data coming from multiple sources, you're going to have race conditions. I think this is pretty solvable, but we've kind of shored it up by there are two methods that you can use. You can either use updated at timestamp as a proxy for the latest revision of this data item, or you can have an auto increment version and then assume that the database will take care of actually the kind of reservation process of incrementing the version, right? In a way that is blocking and so doesn't have race conditions. This approach does have a tendency to have race conditions in the data if you are not at all mindful of it. You may not ever actually run into it depending on how your data is being processed and how your client gets things from the REST API versus listens to the WebSocket API. But there's a potential. So those are some shortcomings in this approach. The too long didn't listen, which is very likely with a talk this long. Real-time API mirrors your REST API, right? Like this is straightforward. This is easy. Don't build a separate transport design for your real-time layer. The client consumer shouldn't care if you're pushing or pulling. When the data gets down to the client, it should be able to react to it the exact same way, either way. That way you avoid geometrically increasing client application complexity. And a data service, in our case, hooks off of the Django ORM, triggers the publishing to those REST endpoints. It's very important that you have a single source of publishing to the Redis pub sub for this to work. And that's pretty much all I had. I think we've got about 10 minutes or so for other questions if anybody has them. Otherwise, this will have only been an 81-minute talk. Yeah.
Hi, do you feel the need to address that authentication may have changed over the lifetime?
The question was, do I need to address changing authentication over the life cycle of the application? Cache invalidation is a hard problem. I have not attempted to solve it. My assumption is that if you at any time were granted access to a REST endpoint, you will always have access to that endpoint. And I've not found a use case, at least for our application, where that's not true, though I could see a use case where it could possibly be true. In that case, you would need a sideband channel to be able to forcibly remove subscriptions from the stream provider. So at the socket.io level, it would need to subscribe to some sort of changed list of ACL in order to say, oh, this user did have access to this endpoint, but they no longer do. I didn't feel the need to introduce that complexity, so I didn't implement anything like that. But that's how I probably would do it. Yeah, what's up?
What was the Node.js server for again?
So the Node.js server part is mainly a publisher-subscriber bridge between Redis. So it consumes from Redis PubSub, and it sends that down via socket.io to WebSockets to the client. right? So there's this piece that sits in between the pub sub on the server and the client sockets. And the client asks Node.js via WebSocket if it can subscribe to an endpoint. Node.js issues a head request to the REST API to determine, can this user subscribe? And if the API says 200, yes, then it goes ahead and asks Redis to subscribe to that channel. And then the bridge is formed between the client and Redis pub sub. So Node is acting as this bridge and this gatekeeper for authentication. Cool. Well, I appreciate your patience in sitting here and listening to me ramble on. So I will give you your 7 minutes back, and I hope you've enjoyed it. Thank you.